on page 4 of our note packs and talking about electron configurations. And what we're studying here is the electron arrangement around the center of an atom known as the nucleus. We are drawing what's called the electron configuration pyramid that helps us diagram atomic structures. At the top of our pyramid, we have our first energy level, n equal 1. We have our sublevel with the spherical shaped cloud and up to 2 electrons. So the first energy level, 1 sublevel with the shape of S-shaped clouds holding up to 2. The second principal energy level has 2 sublevels, an S and a P-shaped cloud. S's can hold up to 2, P's can hold up to 6 electrons. The third energy level has 3 sublevels, the S, the P, and the D-shaped clouds. Those are called orbitals. S's can hold at most 2 electrons, P's can hold up to 6 electrons, and D's with their 5 spatial orientations, each one holding up to 2 electrons for a maximum of 10. We'll draw the fourth energy level. The fourth energy level has 4 sublevels, the S, the P, the D, and the F-shaped clouds. 2 in the S, 6 in the P, 10 more in the D, and the F sublevel, with their 7 spatial orientations, can hold up to 14 electrons. The fifth energy level, has 5 sublevels, but I'm only going to draw in 4 of the 5 simply because we don't have elements that big on our periodic table. I can put it just to show it would be called a G-shaped cloud. We just don't have any electrons in that range. 5D, 5F, and just following the pattern, there would be 9 spatial orientations for a G, giving us 18 electrons. Again, there are no elements that large, we would never hit that. But it does allow me to remind ourselves that the number of sublevels do indeed match the principal energy level. Let's draw in a 6S, 6P, 6D, trying to talk and write, and we'll do 7S, 7P, and that's plenty for our electron configurations. So just as you have done, I'm sure, we've drawn in the electron configuration. What this electron pyramid allows us to do is to follow the diagonal arrows, filling in according to the Aufbau principle. Let me just reflash these. The Aufbau principle, electrons enter the lowest energy level first. The Pauli exclusion principle, an atomic orbital may describe at most 2 electrons, both spinning in opposite directions. And the final rule is called Hund's rule. When electrons occupy orbitals of equal energy, 1 electron enters each orbital until all orbitals contain 1 electron with parallel spins. These 3 rules allow us to write electron configurations. And that word just means the arrangement of electrons around the center of the nucleus of any atom. Now draw with me, if you haven't yet, the diagonal arrow showing the Aufbau principle. What I'm saying is, in order to fill the lowest energy level first, I always put the first 2 electrons in the 1s sublevel. When it's full, we move to the 2s sublevel. 2p, 3s sublevel. 3p, 4s sublevel. Notice how we fill the 4s before we hit the 3d, 4p, 5s squared, 4d, 5p, 6s, 4f, 5d, 6p, 7s, and so forth. The Aufbau principle the diagonal arrows. That's allowing me to know, in order, what's the lowest energy level first, and then begin filling. Let me grab a periodic table a moment. Thanks for your patience. What I wanted to do was to actually use these rules now and do some examples with you. We're going to use the rules, the Aufbau principle, the Pauli exclusion principle, and Hund's rule, and we're going to write what are called electron configurations, and I'll represent the electrons in orbital diagrams for the following atoms. Let me model with you. Lithium. When I find lithium on our periodic table, it's number 3, the atomic number 3. That tells me I have 3 electrons. So I'm just going to tell myself lithium is number 3. We have 3 electrons to place. We start at the top of our pyramid. The first set of electrons are in the first energy level, in the sublevel S, and at most it's holding 2 electrons. When I write 1s2, I've placed the first 2 electrons of the 3 I need to write for. After the 1s fills, we come back to the top and we hit 2s. That third electron will be in the principal energy level 2, in the S sublevel, and I only need 1 more to get to 3. 2 plus 1 give me the 3 electrons we need to write for in terms of the electron configuration. Lithium's 3 electrons, the first 2 reside in the first energy level in an S sublevel, that's a spherical shaped cloud. The third electron is in the second principal energy level in an S-shaped cloud. The electron configuration for lithium is 1s2, 2s1. Now let's show what an orbital diagram is. Now remember, the orbitals have specific shapes. The S-shaped cloud is a spherical shaped cloud on an XYZ axis. The P-shaped cloud, and I'm just going to take some spare room maybe. I'll do it on the back of my paper here. This is something you drew earlier. The P-shaped cloud on an XYZ axis, this could be the P sub X, the P sub Y, and the P sub Z all overlaid on the same set of XYZ axes. But there's 3 different orbitals there, a PX, PY, PZ, and so forth. When I say the atomic orbital, what I'm showing you is a shorthand way of denoting what specific orbital the electrons are in. We don't want to draw the shapes of the clouds each and every time, so chemists have come up with a shorthand. Typically, we draw a box, and that box represents 1 orbital. In the first energy level, the S sublevel, now denoted by a box, so I don't have to draw the geometric shape each time, contains 2 electrons. At most, any orbital may hold up to 2 electrons, and they must have opposite spins. In other words, I'm going to use an arrow to denote 1 electron spinning up, and I'll denote the second electron spinning down. We have a top spin and a bottom spin. The orbital diagram for the first 2 electrons of lithium has now been drawn. The third electron is in an S-shaped cloud. Again, 1 spatial orientation for an S, therefore I'll draw just 1 box. We only have 1 more electron to place to reach the 3 that lithium has, and it really wouldn't matter if you spin it up or down, doesn't matter, I'll just put mine spinning up. The electron configuration, 1s2, 2s1. The orbital diagram, the first box contains 2 electrons with opposite spin. The second box contains 1 electron with a spin up or down. There are 3 arrows denoting the 3 electrons of lithium. Let's try another. Find fluorine on your periodic table, and you'll see it's number 9. Number 9 tells me we have 9 electrons to write for. Remember, every atom has a unique number of electrons, so every atom has a unique electron arrangement called an electron configuration. Starting at the top for fluorine, we start at the top of our pyramid and place the first 2 electrons, 1s2. There's the first 2 of the 9 we have to write for. After the 1s fills, we go to the 2s, and it can hold up to 2 more. There's the 4 electrons. We need to write for 9. So we're at 4. We need 5 more. 1s2, 2s2. Now we come back to the top and we hit the 2p orbital. Now remember, it can hold up to 6 electrons, but I only need 5 more to get to the fluorine's number 9. The superscripts 2 plus 2 plus 5 give me the 9 that we're targeting to write for. Fluorine has 1s2, 2s2, 2p5 of its electron configuration. Let's add on the orbital diagram. Fluorine has one spatial orientation, the s sublevel has one spatial orientation. I place my first 2 electrons there with opposite spin. The second energy level, s sublevel, is holding 2 more electrons with opposite spin. Now remember, the s had one spatial orientation. That's why we're denoting it with one box. But recall what we did for the p sublevel. There was a px, a py, and a pz, all of equal energy. We wrote ourselves a note in the last video lesson. Degenerate means the same. The same energy level. Px is the same as py is the same as pz. Now let me model what I mean. When I place my electrons into the p sublevel, there's 3 spatial orientations. I'm drawing 3 boxes to denote the px, the py, the pz spatial orientation. They're all of equal energy. I know if I have at most 2 electrons per box with opposite spin, but now I get to describe Hund's rule more clearly. When electrons occupy orbitals of equal energy, the word degenerate. One electron enters each orbital until all the orbitals contain 1 with parallel spins. In other words, I place, here we have 1, 2, 3, 4. I have 5 more electrons. I place 1 in each orbital first, all spinning the same way. Then I go back and give a partner. Electron 1, 2, 3, 4, 5. That shows me fluorine has 9 electrons. One of them is unpaired in the p sublevel of the second principal energy level. 1s2, 2s2, 2p5 is the electron configuration for fluorine. Its electron arrangement has been shown with 2 arrows in the s sublevel, 2 in the second energy sublevel, and p down here at the 5th level. The next example is writing for rubidium, the element rubidium. On your periodic table, find with me rubidium, the symbol Rb. What do you find for its atomic number? Rubidium in the first column is number 37. We have 37 electrons to write for. So let me write that out, number 37. So by the time we're done, we need 37 electrons. Starting at the top of our pyramid, we write out 1s2. There's 2 down, 35 to go. From 1s2, we fill the 2s orbital with 2 electrons. We then move to the 2p6, 3s2, 3p6, 4s2. Let's count. 1, 2, 3, 4, plus 6 is 10, 11, 12, 18, 19, 20. So we're at 20. From 4s squared, we go up to the top and find 3d10. That gets us to 30. From 3d10, we hit 4p6. There's 36 electrons and 1 more to place, and it goes in the 5s sublevel, and we have just one electron there. Electron configuration for rubidium: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1. If you add the superscripts that represent the number of electrons contained in each electron orbital, that gives us a total of 37 electrons. Let's also write the orbital diagram. The s spatial orientation in the first energy level can hold 2 electrons, one spinning up, one spinning down. The 2s orbital, with its 1 spatial orientation, holding 2 electrons, one spinning up and one spinning down. There are 6 electrons in the p sublevel, so I need 3 degenerate orbitals, a px, py, pz, 3 different spatial orientations. Place 1 electron into each orbital first, and then go back and give a partner. 1, 2, 3, 4, 5, 6. So all spinning in an opposite direction. 3s2, 3p6, 1, 2, 3, 4, 5, 6. 4s2. Now with the D's, we've not drawn one like this yet. The D's had 5 spatial orientations. I have to draw 5 degenerate orbitals. 1, 2, 3, 4, 5 spatial orientations for the D's. Place 1 electron into each orbital first, and then go back and give a partner. So that's getting crowded, but there are 10 arrows, 5 spinning up, 5 spinning down. After 3d10, we get 4p6. And then finally, 1 electron in the 5th energy level, spinning up or down. It doesn't matter because it does not have a partner. We have drawn 37 arrows into different orbitals that reside around the rubidium nucleus. Electron configurations really are just nothing more than a description of the arrangement of electrons around the nucleus of an atom. Your example 2 asks you to keep going. Writing the electron configurations for each of the following indicate how many unpaired electrons the atom has. You should pause the video and work through these examples. Use your electron configuration pyramid, writing for the number of electrons that each atom contains, and when you are ready, start the video again to check your work. Do them first. Don't cheat yourself of the practice. Here's phosphorus. Number 15. We have 15 electrons to write for phosphorus. Starting with the lowest energy level first. 1s2, 2s2, 2p6, 3s2. Let's see. 1, 2, 3, 4, plus 6 is 10. We're at 12. We need 3 more. So 3p, 3 electrons in the 3rd energy level. If I add the superscripts, we should count to 15 electrons. 1, 2, 3, 4, plus 6 is 10, and these 5 give me the 15. Draw the orbital diagram. 2 electrons in the 1s sublevel with opposite spin. 2 more electrons in the 2s sublevel with opposite spin. 6 electrons in the p sublevel contained in each of those 3 orbitals, a px orbital, py orbital, p sub z orbital, give us 6 electrons. Here's the 3s sublevel with its 2 electrons. And finally, those last 3 electrons, 3rd energy level, in the p sublevel, we have 3 electrons to write for. Remember the rule, place 1 into each orbital first before you give a partner, all spinning the same way. That was called Hund's rule. Electrons occupy orbitals of equal energy. Place one into each orbital, all with parallel spins. We have 3 unpaired electrons in the phosphorus atom. Let's write for nickel. Nickel is number 28. We have 28 electrons to write for. Starting with the lowest energy level, the 1s2. After the 1s2 fills, we fill the 2s. After the 2s fills, we fill the 2p, then the 3s. Let's count. We're at 10, 11, 12. After 3s, we hit the 3p. After 3p, remember we're following the arrows down, not rows going across, but the Aufbau principle has us follow the arrows down. We hit 4s2. Let's count again. 2 and 2 is 4, plus 6 is 10, 12, 18. We're at 20. Remember how we had 28 to write for? After the 4s, we start filling the 3d orbital. To get to our target of 28, we only need 8 electrons in the third energy level of the d sublevel. The electron arrangement shows 2 electrons in the first energy level in the s sublevel. 2 more electrons in the s sublevel of principal energy level 2. 6 electrons in the 2p sublevel. 2 more electrons in the 3s sublevel. 6 electrons in the 3p sublevel. 2 more electrons in the 4s sublevel. And now these 8 electrons in the third energy level of the d sublevel, remember the d's? 5 spatial orientations, 5 degenerate orbitals. 1, 2, 3, 4, 5 degenerate orbitals. I place 1 electron into each orbital first, all spinning the same way. Then I go back and give a partner. There are 2 unpaired electrons in a nickel atom. These 2 in the third d sublevel are unpaired. How'd you do for carbon? Carbon with its atomic number of 6. Number 6 would go 1s2, 2s2, 2p2. 2 plus 2 plus 2 is 6. 2 electrons in the s sublevel of the first principal energy level. 2 more electrons in the second principal energy level, s sublevel. And I must still draw all 3 orbitals. P's have 3 orbitals, even though one will be completely empty. We must draw it to show we know 3 spatial orientations, px, py, pz. There are 2 unpaired electrons in a carbon. 2 unpaired, this guy completely empty. And one more that was called argon. Argon number 18. 1s2, 2s2, 2p6, 3s2. See, I'm at 10, 11, 12. 3p6, 1, 2, 3, 4, 10, 12, and 6 is 18. The electron configuration for the 18 electrons of argon. The orbital diagram shows 2 electrons in the s sublevel, 2 more in the second energy level of the s. Whoops. Here's my p sublevel for the second energy level. Here's 3s2 and 3p6. There are 0 unpaired electrons. In other words, all of them have partners. Friends, that's interesting to a chemist in determining bonding. How many open electron orbitals helps us predict how atoms bond when they come together to form compounds. Before we flip over, let's take a quick peek at what we've learned. There are 3 general guidelines to help us follow electron configuration rules. The Aufbau principle, follow the diagonal arrows. When we write out our electron pyramid, the Aufbau principle shows us the lowest energy level is on a diagonal line in our pyramid. The Pauli exclusion principle. An atomic orbital can hold at most 2 electrons, both spinning in opposite directions. Each one of these little boxes I've drawn here represent an orbital, and at maximum I can only place 2 arrows. Each arrow denotes an electron. Hund's rule: when electrons occupy orbitals of equal energy, 1 electron enters each orbital first, all with parallel spins, before you go back and give a partner. Place 1 electron into each orbital first before you go back and give partners. When we write out electron configurations, our superscripts denote electrons, where the electrons live outside the nucleus of an atom. Since every atom has a unique number of electrons, every atom has a unique electron arrangement, which means a unique electron configuration. Pause your lesson here and be sure that you're solid on those lessons.